Okay, we have discussed Coulomb's force and its applicability for only point and static charges. Now we will discuss Coulomb's force due to continuous charge distribution. Now continuous charge distribution may be considered to be a system comprising of infinite point static charges. Right? We can categorize into three different types: 1D, 2D, 3D. In one dimension, it's linear charge distribution, whereby the charge is uniformly distributed over a line. Two dimension, it is surface charge distribution. Here the charge is uniformly distributed over an area. And in third scenario, three dimensional, we'll consider the charge to be uniformly distributed entirely over a body, solid body, throughout its volume. So, continuous charge distribution, it can be linear, it can be surface charge distribution, it can be volume charge distribution. Linear means, just as I've told you, suppose this is a thread or any line and charge is uniformly distributed over here. It's a linear charge distribution. Net charge Q, it's distributed uniformly over length L. It can be a straight line or a curved line. Surface charge distribution, there's any area. It can be any symmetrical shape or any irregular shape area, flat surface. And here charge is uniformly distributed. Suppose S is the surface area and Q is the net charge, which is distributed uniformly over this surface. So it is the case of surface charge distribution, two-dimensional case. Over here, there is any solid body of any shape, and here the charge Q is uniformly distributed throughout the volume of the body, which is considered to be capital letter V. So that's three-dimensional case, right? Here we will make use of the term lambda. It is known as linear charge density. It is known as linear charge density. It is defined as charge per unit length. Lambda is linear charge density and it is known as linear charge density. It is defined as charge per unit length. The charge uniformly distributed per unit length. So its SI unit would be coulomb per meter. Here we will make use of the term sigma. It is known as surface charge density. It is defined as the charge which is uniformly distributed per unit area. So SI unit would be coulomb per meter square. Over here the charge is uniformly distributed over the volume. So we'll make use of the term rho. It is the volume charge density. It is defined as the charge per unit volume. So its SI unit would be coulomb per meter cube. So now let's imagine a point static charge to be placed over here, Q naught. And consider some elementary portion over here. We can consider it to be dl. And since the charge Q is distributed uniformly over the entire length L, then the charge contained in length dl may be considered to be dq. And suppose the distance between the center of the elementary portion to this charge Q naught is r. And for convenience, let's consider both are of like charges. Then it will experience a force away from it. It will experience a repulsive force. And that small force experienced by Q naught due to small charge dq would be represented by df along this direction. That's clear. We can extend the same thing over here. Consider an elementary area. Total area is S, so that elementary area may be considered to be ds. And net charge is q, so the small charge under consideration will be considered to be dq. And the distance between the center of this elementary portion to this charge Q naught is r. Again, as per convenience, we are considering both the charges to be like ones, therefore it will experience a small repulsive force. So charge force experienced by Q naught due to the small elementary vanishingly small charge dq would be df. Right? Over here, again a small elementary portion. Net volume is V, so the volume of this elementary portion can be considered to be dV. Net charge is Q, uniformly distributed over volume V. So charge distributed over the small volume may be considered to be dq. And the distance may be considered to be R. Again, it will experience a small repulsive force represented by dF. Right? Now let's try to represent this dF. Its magnitude would be 1 over 4 pi epsilon. We are considering the charges to be placed in aero vacuum. One of the charges Q naught, the other charge is dQ, and the separation between them is R. So this is the magnitude. And if you write it in the vector form, then you can write it over as R cap. And R cap can be replaced by vector divided by its magnitude. That's okay. So in turn, it may be written as Q naught dQ divided by 4 pi epsilon RQ R vector. This we have discussed, Coulomb's law in vector form. So either write R cap or R vector divided by R, so that will change the expression with this form, right? Similarly, over here. So, again, these two charges are assumed to be placed in aero vacuum. So it will be 1 over 4 pi epsilon naught. In case it is placed in medium, then epsilon will get replaced by epsilon, which will be the permittivity of that particular medium under consideration. So one of the charges Q naught, the other charge is dQ. Separation between them is R. So this is the formula K Q1 Q2 by R square. That's the formula for the magnitude of the electric force between two charges. This is the magnitude. What about its direction? Suppose R cap like this. So this will give the direction of dF. Now what I've stated earlier is unit vector. It's a vector divided by its magnitude. So it may be written as, right? Or R square into R, it will become R cube. Clear? Similarly, over here, dF vector, it may be written as 1 over 4 pi epsilon naught. One of the charges dQ and the other elementary charges Q naught. Distance is R square, again R cap. Unit vector is vector divided by its magnitude, so it can be also written in this particular manner. Clear? Okay. Net force. Now, net force over here. So what we will do is, it can also be represented in terms of lambda. Lambda is Q by L. In case of elementary charge, lambda may also be written as dQ by dL. So dQ may be replaced by lambda into dL, right? So what to do is, it can be replaced by lambda dL divided by 4 pi epsilon naught R cube R vector. Over here, this is surface charge density. For elementary charge dQ distributed in area ds, sigma may be written as, in calculus it may be written as dQ by ds. So dQ over here may be replaced by sigma into ds, right? So what do we get is 1 over 4 pi epsilon naught Q naught, substitute the value of dQ over here, sigma ds. Fine. And similarly over here we can write Q naught in place of dQ, we can write rho into dV. So rho dV divided by 4 pi epsilon R cube R vector. So this is the elementary force experienced by charge Q naught due to the elementary charge dQ. In order to find the net force experienced by this charge Q naught due to the continuous charge distribution, whether it is line charge distribution, surface charge or volume charge, we'll integrate it. So net force over here would be integration of this. So constant can be taken outside the integration. Q naught is constant, 4 pi epsilon naught is constant, lambda is constant. So it is dl by r cube r vector. R can't be constant because if you consider elementary portion over here, then the distance of the observation point from this elementary charge would be varying. So it can't be taken outside the integration. Right? So, and this is known as line integral, single integration of line integral. So this is the expression for the force experienced by charge Q naught due to this line charge distribution. Similarly, in case of surface charge distribution, the force experienced by Q0 due to this entire surface charge distribution would be given by integration of this. So integration of df is f, constant, it can be taken outside the integration, so Q0 sigma is constant, 4 pi epsilon, and this is double integration, ds divided by r cube r vector. Double integration, it represents surface integral. There's another alternative way. If you represent only by single integration, just write over here as S. This is the surface integral. Integration ds means surface integral. So this is the expression for the force experienced by charge Q0 due to this surface charge distribution. Right? Over here, due to volume charge distribution, it would be given by again integrating the same thing. 4 pi epsilon r cube. It will be dV by r cube r vector. So this is the expression for the force experienced by charge Q0 due to this volume charge distribution. And over here it is the volume integral. It can be either represented like this or it can be represented by triple integration. That will represent volume integral. So this is the expression for the force experienced by charge Q0 due to line charge distribution, due to surface charge distribution, and due to volume charge distribution.